we try to make this session little different. If you have the laptops, you can use the laptops for execution of the codes. I will give you the links also. So, let us start with the session. This is the session 6. In the last 5 sessions, not 5, 4. First one is introduction part and how the workshop will be conducting and all. And from the second session onwards, the actual concepts are started. And we started from the ground because you have just completed the ML. Just completed the ML, that is IML, Introduction to Machine Learning. Hope all of you have done that course. And then immediately you have to enter into the projects. Entering into projects, it is not an easy task. So because of that reason, we planned to give the flavor of all the concepts in the deep learning and the generative AI. Of course, generative AI means it is a separate concept, and it is some intersection point is there from the deep learning and this generative models, right? So if you combine any concept with machine learning or deep learning, it will give you more power because of the power of deep learning, right? So as the part of that, the deep learning, the base for the deep learning is the ANN that we have covered in the previous, in the last day's session. What is ANN and what are the layers and all we have covered. And then CNN, convolutional neural network, we have covered that. I will give you the connection and the flow between all these concepts at a glance, and then I will enter into today's session, right? Now, I hope all of you know this. Can you recognize this? We are trying to recollect this, somewhere we have seen this, right? Where you have seen? Regression, yes, okay. So regression, the regression, I think you know the equation also, you know that very well, and it is a linear. Even in the regression, it is a linear regression. Why? Because the relationship is linear. You can fit a straight line so that you can predict the required value by passing the known value x and y, right? Now you have another kind of algorithms also there. What is this? Logistic. We can say that it is a classification, binary classification. We can say that it is a binary classification. Where it is coming from? This one. By using this equation only. We are using the same equation to get this S curve. Am I correct or no? See this. The equation is, it is from the linear only. Meaning that we are coming with the non-linear relationship from the linear. We have the linear and non-linear relationships, right? The linear relationship, we can convert that into non-linear by applying the logistic regression. Please keep it in mind, these two concepts. Now I am changing this. Now, can you represent this model like this? Sigma Wi(xi). What is Wi? That beta 1, beta 2, whatever we have specified, that is, the beta is representing as W here, right? And then, this is the linear only, linear model. And I want to apply this part. How can we apply this part? This is by adding the sigma, right? Now we can apply this sigmoid method so that we are having, this is a linear summation and activation, two parts. We can take the algorithm, the logistic regression algorithm, in this way, like a bubble. It is like a bubble. It is one unit, right? It consists of the summation, linear summation and activation. The combination of these two will give you one unit, right? And it is taking the inputs x1, x2 and so on, xn, and it can produce the outputs. If it is the classification, here I am taking the binary classification, so probability for 0 and 1. It will give you the probability for 0 and 1. So either 0 or 1 it will be given. Hope you understand, right? Now in this, I have this model, number of inputs are there and it is producing the outputs. In some situations, this analysis is not sufficient. If the number of inputs are more and relationship is more complex, a single node or single unit of the algorithm, machine learning algorithm, it cannot handle this situation. So in that case, I want to repeat the same, whatever we have this unit, I want to repeat the same unit, replicate the unit number of times, and the same input will be given to all these units also. Now can you give the output? All these are giving separate outputs, am I correct? So which output I have to take? So I have to aggregate this. To aggregate that, I have to take one more node and we can connect them, and then the final output can be given from that node. Now in this case, this is called, this is the hidden layer, it will become as the hidden layer. Now you can add any number of units, the unit is called, we can call it as the node. You can add any number of nodes and any number of layers also. This is one layer, this is one layer, this is one layer, and you can add one more layer and one more layer. You can add any number of layers and then you can get the output. So if you increase the number of layers, actually this is called the artificial neuron. This is representing the artificial neuron. Neuron means it is in our brain. Artificial neuron. Actually biological, actually it is looking like biological, but it is not based on biological. Please remember that. It is completely based on the mathematics. Completely based on mathematics and matrix multiplications. Matrix operations. Most of the concepts are from the matrix operations. It is a mathematical term. Your machine learning is completely based on the statistics. And this is based on the mathematics more. Right? So, you can increase the number of layers. You can add the number of layers to increase the complexity, to find the complex relations. If you have very large data set, if you have 500 inputs, and if you want to find the relation, even if you have 500 inputs, a simple logistic regression can find that, can easily handle that. But in some situations, even if you have 5 parameters, a single unit may not be able to handle that. It may not be able to analyze. In that situation, you should go for this. But you need not go for simple situations, simple solutions. You need not go for the neural networks, ANN. You need not go for the ANN for all the situations. It is like using flight or helicopter to go to Warangal from Hyderabad. Is it correct? No. It is better to go by road. It will take much time to go to the airport and some helicopter point or all this that will be there, helipad and all, right? So, if it is possible to solve the problem by using a small algorithm, better to go for that. If it is not able to find the solution in the simple algorithms, then go for the higher level. Now in this, in the neural networks, artificial neural networks, we can handle the data which is in the tabular form. That is easy to handle. And if you have the image data, in the last session, we have done this, right? In the last day, afternoon session. See here, we have the image. How the image will be represented? If you are able to understand this point, it is easy to understand remaining concepts easily. We can represent the image in the form of the numbers. What are those numbers? What are those numbers? How can we represent the numbers, the image? Let us take the black and white image initially. The black and white image, now I think you are having the mobiles and phones, the laptops. You just see that screen very near for 2 seconds only 2 seconds please. Now only, you just see that. Very near. You see your screen very near, not more than 2 to 3 seconds. Your eyes will be affected. What did you find? Small blocks will be there. Squares. You will get the squares. If you see that very near to your eye, you will get the small blocks. They are called the cells. See here, you are seeing that here. Like this, you will get the blocks. Each block, that is the cell can have some data. You can take that cell as one byte. If you take that as one byte, what is the maximum value can be stored in that? 1 byte. 8 bits, okay. What is the maximum value you can store? What is the range of 1 byte? Range of 1 byte. Is it 0 to 255? See, you are learning generative AI. If you forget the basics, it is very difficult. 1 byte means it will take 7 bits. 1 bit is reserved for sign. So, minus 128 to plus 127. So, it is a range, and in that also you can see that if you make that sign bit also for data, then 0 to 255. So, the data will be within that one cell, the value will be from 0 to 155 maximum value, the range. Now, the intensity will be stored there in that cell, 0 to 255. That value will be stored. For each cell, the values will be stored. If it is 0, then it will be black. If it is 1, it will be white. Black and white. In between, if it is 100, then it will be gray color. And there are number of shades, the combinations, right? Number of shades, 255 shades will be there. So you will get that in this, it was represented in a simple way. See here, these are the white cells, white, and this is the black, and this is the gray. You can see that white is representing with 1, 1, and black is representing with 0, 0, and dark gray is representing with 0, 1, and light gray is representing with 1, 0. I think you understand. Your screen is organized like this. The picture is organized like this, meaning that the intensity of the color that will be represented. This is for the black and white. And if you go for the color, the same strategy but RGB. This was also explained in the last session. But only the thing is intensity of the color. What is the intensity of the red? What is the intensity of the blue? What is the intensity of the green? The combination will give you the new color. So that is the representation of this. Now in this way, how can you represent one image, black and white image? How can you represent a black and white image? I have a black and white image. What is the data structure to be used? Data structure. Huh? Data structure means any library you can. In Python. Huh? NumPy. By using NumPy or two-dimension array. By using two-dimension array, you can represent this. Right? And if you want to represent the color picture, then 3-dimension. 3-dimension means it is not 3-dimension picture. It is having 3 layers, that's it. Only 3 layers. Red, green, blue. Red, green, blue will be there. So, the intensity of the red, intensity of the green, intensity of the blue will be represented for each pixel. So, because of that reason, you can handle the images by using the numbers in multi-dimension. Please remember this. Okay. Now, if you want to analyze this, now you have to pass this. If you pass the regular tabular data, then each record will be sent to the XY, X1, X2, X3 and so on. Let us say for example in your California, regular example is I think California dataset, right? In your IML, for regression you have taken California dataset or iris dataset. If you take the iris dataset, then X1, X2, X3. For iris dataset, it is sepal length, sepal width, petal length, petal width. X1, X2, X3, X4. But in this, what is that? It is the pixels. Each pixel you have to take. It is in the 2-dimension space. It is in the 2-dimension space. How can you take that? How can you give that into the machine learning library? That you have to convert into the single dimension. See this. All this first row has to be given. After that second row has to be continued and so on. The last pixel, it will be the last input. Right? Now in this way you can analyze and you can add any number of layers and you can analyze that, you can classify. Clear? Now this is not sufficient because if you want to analyze the picture, please think in different way. If you want to analyze the picture, meaning that image, the image pixel that will be depending upon the left side pixel, right side pixel as well as the top, bottom and diagonal, opposite diagonal. Am I correct? If you take one spot in the entire image, that is depending upon the surrounding pixels. The surrounding pixels are not covered because it is taking in the linear fashion. So, it cannot cover the surrounding pixels. To cover the surrounding pixels, to analyze the surrounding pixels also, we are going for the convolutional neural network, convolutional layer. Now, if you go with this is the 2-dimension space. This 2-dimension space can be analyzed. See here, I am taking a small kernel and one more problem is weight explosion. Weight explosion means in the previous case, if you see this, how many? X256. For each and every node, for each X, you will have W. WIXI, formula is WIXI. So for each X value, you should have W. So, how many W's are there? And for each node, you should have those many. X is 256. 256 for this, 256 for this, 256 for this. In that way, if you have 5 nodes, then 5 into 256, those many parameters required. In this way, if you increase the number of layers and if you increase the number of units, then there will be the weights explosion. Millions, trillions of weights will be generated. It is not possible to calculate these many operations because the matrix multiplication, it is very difficult to perform the matrix multiplication on CPU, right? Or in the any processing unit, it is very difficult. So because of that reason, to simplify that, instead of taking how many units you have to take now here, in this you have to take total 256 for each node. Instead of 256, I can take just 4 in this, 4 or 9. 3 by 3 kernel. By taking the kernel, I am applying that on that. See here, A, W, B, X, corresponding elements will be multiplied and find the summation, so that you will get one pixel. So from the 3 by 4 picture or image, you will get 2 by 3 image. So it is reducing. So it is reducing the dimension and also getting the intensity. It is analyzing, right? So this is the convolutional neural network. What are the advantages we are getting from this convolutional neural network? One is we are sharing the weights. The same kernel, it is moving over the image. The entire image will be analyzed by only, for in this example, the entire image is analyzing by only 4 weights. Actually, how many weights are required? For this image, 12 weights are required, because 12 pixels are there. So 12 weights required. Instead of that, we are using just 4. So weights are reduced. And one more thing, these weights are analyzing entire image, right? So that is the advantage here. We are reducing the number of weights and we are considering the neighbors: left, right, top, bottom, diagonal, opposite diagonal. Generally we will take 3 by 3, 5 by 5 kernels, not 2 by 2. This is only for simplify and to explain we have taken this. Generally we will take 3 by 3, 5 by 5, because middle element, from the middle element surroundings will be 8. From the middle element surroundings will be 5 by 5, 25, 24 pixels will be there surroundings. So like that we can take. So this is about the convolutional neural network, right? And so this is how the convolutional neural network, yesterday we have seen that, in the last session we have seen that. Clear? Now in this, see, we are taking 5 by 5 image, 5 by 5 image, we are applying the 3 by 3 kernel, it is moving on the 5 by 5 image and we are getting 3 by 3 image as the output. That image is the feature. The output of the convolutional layer is called the feature. The intensity or the edges, whatever the features are there, it may be the edge. What type of feature it is taking, we don't know. That will be analyzed internally, right? Now, yeah. Moving back, I just want to show you one small video on this. Just to understand.
When you're launching a new product with a tight deadline, 2 weeks? Grammarly's tone suggestions.
Yeah, you just have a look on this, how the convolution is going on. It is taking this part, it is a kernel, it is applying on these area and then it is performing this, it is calculating this pixel. This pixel is calculated by these elements. From where it is taking, it is showing clearly. I hope you understand, right? So it is reducing the image size and yeah, see this you can understand very clearly. The picture is having A, how it is convolving and how it is creating the features. It is creating the features by applying the kernel, 3 by 3 kernel. By applying the kernel, it is moving the kernel over the image. Each and every pixel is analyzing. Right? And then next, second feature, meaning that number of features are generating. and all those features later, all those features will be analyzed, and next level will be also there. It will be shown. See, number of features by applying the number of layers, and finally we will get the final layer here, final features. From there, the original, the output, it will be verified with the original output. The features, the extracted features, they will verify with the original output pattern. So if it is equal, then if it is matching with A, 92%, so it will be given. Hope you understand. So this is the working of CNN. Now in this case it is okay. Oh, sorry.
AI can now tell you which Excel formula.
Okay.
To support the production of more high-quality content, consider supporting us on Patreon or YouTube membership. Additionally, consider
Yeah. Yeah. So I hope you understand the convolution concept. And now by using this convolutional layers, we can analyze the pictures, right? In this, you are having the number of features here, and convolution 1, convolution 2, and so on. We will have the flatten. Once if you flatten, then we can go for the dense layer, one more dense layer, to classify what is the object. See, please remember that the convolutional layers will be only here only. Up to here only there is the convolutional layers. They are only feature extractors. We will not use them generally for classification. They are only for the feature extraction. The classification will be done by the dense layers only again. Okay. In this, now we will use the softmax activation. If it is the two classes, you will give the sigmoid activation. If it is having more than two classes, you will give the softmax, number of classes, multi-class classification, you have to give the softmax activation. Hope you understand. Now my intention is not this. This is okay, classifying, it is classifying very nicely. If you give a picture and if you want to analyze whether the dog is there in that picture or not, it will give. And where is that particular dog? In the entire image, where is the dog? You want to localize that. If you want to identify the spot, then that will be the object detection concept. It is another wing from the CNN. From CNN, you can go to another wing that is called the object detection, YOLO and all this. That is another wing. One more wing is also there. That is called the regeneration of the image. Regeneration of the image. That is what we have to concentrate in this session. Right? Now from here, CNN. Okay. Now we have the CNN. How many layers you have to add? Do you know that? How many layers? And in each layer, how many kernels or how many filters you have to add? We don't have the idea. Randomly you have to select. Trial and error. First you have to take 2 layers with 64 nodes and 128 nodes, and then try with that, check the accuracy, and again add one more layer, check the accuracy, add one more layer, check the accuracy, remove one layer, accuracy, like this, trial and error based only. And you have to do so much of research, and some combinations are very good for some type of data sets, some combinations are good for some other type of data set. Let us say for example, our regular data sets, dog, cat classification. For that, some simple network is enough. And if you want to go for the biological or satellite images, then you have to add more layers. That is called the deep. If you are going depth, then it is called the deep neural network. That is called the deep learning. Right? Now, again there are some standard formats. How many layers are there? And how many nodes in each layer? For that also there are some standards. So the standard architectures are also designed. See here, like ConvNet, LENet. LENet is having some number of layers, 5 layers, let us say for example. 5 layers, first layer should have, and input should have 28 by 28 size. Meaning that 28 pixels, 28 pixels. And next level, first layer should have these many, let us say for example 16 nodes. Second layer should have 32 nodes. Third layer should have 64 nodes. In between I want to add the pooling layer and all these. This is the standard structure. There is a standard structure for LENet, and in the same way AlexNet, GoogleNet, VGG 16, VGG 19. VGG 16 means 16 layers will be there. VGG 19 layers will be there. In the similar way, we have some other architectures also like ResNet, residual network. Residual network means we will add the same image to the features. So that is another big case study that you can identify that. So ResNet, the ResNet you have the 50 layers and hundreds of layers also possible. For that you need high-end processor, right? And these are the various standard CNN architectures available, and all these architectures are used for classification, and they have tested on some data sets. For some data sets they are giving very good result, right? All these are feature extractors, and final layers are the dense layers which are added for classifying the images. That's it. Classification of the images. Right? Now, my intention is, see here, this is the same thing. This is the classification. Now, my intention is not this. I want to regenerate the image. Whatever the image I have given, I want to regenerate the image here. I don't want to identify that. For that, what we can do is, we can create the mirror image or mirror architecture on the other side. When you get the dense layer, from here onwards you have to resampling or upsampling. From here you are going for the convolutional layers, and you have to do the reverse operation. Convolutional means, you have seen that previously, you have seen that 5 by 5, if you apply the 3 by 3 filter on the 5 by 5, it is coming to 3 by 3. Again if you apply 3 by 3, it will give 1 by 1. So like this, it will reduce the convolutional layer, it will reduce the image size. The dimensionality will be reduced, right? And number of features may be increased. Okay. Now, from here onwards, you have to regenerate from one pixel, you have to generate 3 by 3 pixels. From that you have to generate 5 by 5 pixels. And then next level. So like this 7 by 7 and so on. So in this way you have to increase the image size and regenerate the original image. Here you are giving 28 by 28 by 1 and I want to get again 28 by 28 by 1. We have to generate the architecture like this. Hope you understand. Right? In this, see here, this is called the deconvolution. The convolution, it will extract the features, and deconvolution, it will increase the size. It will increase the size. For this again there are so many algorithms. There are several techniques to regenerate the images. One technique is upsample plus convolution. You have to apply the upsampling and convolution, combination of upsampling and convolution. Of course, padding is also there. In the last session we discussed. Padding means what is the image size you are giving, the output will be also same without reduction. So we can give the convolution with padding plus upsample. Upsample means 3 by 3 will become as the 5 by 5. The last pixels will be repeated. The corner pixels, the edges, they will be repeated and apply the convolution on that, so that you will get the new image. Or directly deconvolve, that is convolution transpose, that is also available. Direct layer is available, and there are so many techniques are there, so many algorithms are also there how to generate the image. But simply we can use upsample or deconvolve, that is the convolutional transpose, conv 2D transpose. 2 dimension, we have to use 2 dimension only. Why? Because we are using the 2 dimensional images. What is the 3 dimension image? 3 dimension image. MRI scans. Example is MRI scan. MRI scan is the MRI scan report. If you see that, the organ, see here, if you see this object, this mic, from this direction you will get one shape. From this direction you will get one shape. From this direction you will get another shape. So for that the dimension will vary, right? So the 3 dimension means MRI scans. Example, simple example is MRI scan images. And here we are using simple 2 dimension image only, but only to represent the 3 colors we are giving the 3 layers. But it is the 2D images only. Now we have to reconstruct this. How can we reconstruct this? And here we are having the technique. Here we are generating. Now we can see that. And if you generate like this, whatever the features are extracting, this part is called the encoder. It is encoding. If you give 255 by 255, and that will be given into 10 by 10 vector. What is this? Here this is called the latent space. In the latent space you will give a small vector. You can give a small vector with a 10 size, meaning that this entire 28 by 28 image, that can be represented by this 10 vector, 10 values. And as Neil sir said, you can encode this. Instead of 28 by 28, you can send just 10 bytes over the network. And on the other side, you can apply the decoder. How we have to train the decoder and encoder is, it should be properly encoding, and the decoder should be able to get back the image by using this small latent space. With the small vector, it should be able to regenerate. Clear? I will give you a small example. I have seen one painting somewhere. I cannot bring that painting because it is very big. So what can I do? I have to see there, and I have to come here. I have to try to draw this, reconstruct. And if I am very well trained, then I can reconstruct it very easily. Regenerate. I can regenerate the image. Once I draw that, if there are some problems, then again I can go back, and again I have to see that and update my memory, and again come back and again retry up to I get the original image. At least minimize the error, right? So meaning that with the small size you are able to generate the entire image by using a small vector. That is the idea behind this. So what is the size of the latent space vector you are taking? That is playing the important role. If you want to generate the complex pictures, then you have to take little big. And if you are going with this picture, this example, it needs how many vectors, do you know? Can you imagine how many vectors required for this? How many vector values required? I mean, how many values in the vector size? Just 2. With just two values, the size is 2 here. With only 2 bytes, you can represent this 28 by 28 image of this. You can regenerate this. And if you want to recognize the face, regenerate the face, then number of features are there. So 2, it is not sufficient. You have to go for 100. You can go for 200. If you increase the size of the latent space, this space, if you increase this space, then the complexity will be increased and more computing power is required. Hope you understand. Are you getting? Right? So, now we have to, yes, this is the encoder and this part, regeneration of the image, that is called the decoder. In between there is the latent space, that is simply a vector. This is the autoencoder. This is the autoencoder. Now in this, what is the autoencoder? It is a neural network made up of two parts, encoder and decoder. And encoder network, it compresses the image into a vector, and decoder, it regenerates the image from the compressed vector. From the compressed vector, it should be able to regenerate the image, right? And of course, the network, what you have to train? The model. The model has to be trained to get the proper compressed vector, that is the training of the encoder, and you have to train the decoder to regenerate the image properly. Right? These are the two things. See here. And this is also called the representation vector. This is also called the representation vector. Whatever we are taking this, see here, only two values. Representation vector. That is called the representation vector or latent space. In the latent space, we can have the representation vector. Clear? Yeah. Next. Now, the representation vector, it is the compression of the original image into lower dimensional latent space. In the latent space, it will be having that. And choosing any point. Here we are having 2 points. You can start from any point. You should be able to generate the image. You can take any one of the point, any point, and you should be able to generate the original image. Your model has to be trained like that, right? And increasing the dimensionality, latent space, obviously it will increase the complexity and it will give more problems also. What are the problems? You will see that practically. Okay? Now, so see here, and autoencoder, in the autoencoder, encoder, how can we build the encoder? First of all, you have to work with, if you want to work with the encoder or autoencoder, you should have the knowledge on how to build a model, CNN model. If you want to design the CNN model, you should know how to build the ANN model. Because of that reason, we have to start from ANN. This is a stepping stone. We can say that it is a stepping stone for generation of the generative AI. First step in the generative AI. Right? So, in this, first of all, how to create the model? There are so many techniques to develop the models. You have different libraries also. So many libraries like TensorFlow, PyTorch, Keras, and DNN and NN, and even in our scikit-learn also we have the neural network concept, neural network packages available, right? So many libraries are available, and as you know that, I think you can observe that the machine learning means only one unit, it is having multiple units. So computation power is, more computation power is required. Because of that reason, we have to use the GPUs. GPU. Whatever you are using the graphics card, you are having the graphics cards in your laptops. Why we are using the graphic card? To play the games and to watch the movies with full clarity. We are taking the graphics card only for that purpose. Am I correct or wrong? If there is no graphic card, no, I don't want this laptop. But what is the purpose of that graphic card? We don't know. The purpose of that graphic card is supporting to the CPU. It supports the CPU to calculate the graphics. Graphics means just now I have shown that the image is representing with the numbers and multi-dimensional space, multi-dimensional array. So how can we calculate that? That we have to calculate in the parallel. If you work with the CPU, then it will be sequential process. If you add the GPU power to that, it will be the parallel process. How to parallelize that? How to parallelize? That is by using CUDA. The GPU will work with CUDA. We cannot write the programs on CUDA. It is very difficult. We cannot go for agriculture. We cannot go to agriculture and you cannot build a crop and you cannot take the rice grains and all. We are just taking that, and you should know how to cook. You cannot depend on the restaurants or hotels, or you cannot go to the direct agriculture. We are in between. So at least you have to know something about the agriculture, and at least you know what is the taste in the restaurant. Then you should be able to cook so that you will get number of flavors. Right? In the similar way here also, you cannot go from the completely ground, that is completely mathematics and by using CUDA programming and GPU architectures and all. No, we don't have that much time. So we have to use the predefined libraries. On top of this CUDA, we have the TensorFlow library. TensorFlow, which can be used for accessing the GPU very easily. You can work with GPU without any system level code, right? And Keras. On top of that, again there is a Keras, one more layer. So it will make your life easy to build the model. So you should build the model at least. You should be able to tune the model at least. If you are not able to build the model, at least you have to tune the model. If you want to tune the model, you know this concept, how to build the model first and how to add the layers. So what is the first step is, we have to define the input. Input is also one layer. Input is also defined as one layer in the TensorFlow or Keras. So we have to define the input layer and stack of convolutional layers in the sequential, because all these are sequential only. The autoencoder is sequential. Please remember this. Autoencoder can be developed as sequential, because in the sequence of convolutional layers, and at one place there is the vector, and from that reconstruct the image, regenerate the image by reshaping and also upsampling. Okay, so stack of convolutional layers, you have to go with that for encoder, and then finally you have to flatten that. Very good design of the network is, you need not go for flatten. If you are able to build the model in that way, your model will work very fine. Meaning that anyway convolutional layer, it is reducing the image. If you are able to build the model up to 1 by 1, up to you get the picture of 1 by 1 size, if you are able to develop that type of model, then that will be very good. And then of course you can flatten it only for namesake, and then you can redesign it. Okay, and then flatten. Of course, so many models are not following this rule. There is a traditional rule, but nobody is following. Generally, up to 28 by 28. Once if you get the 28 from 255 by 255, if you get the 28 by 28, we are just flattering it and reconstructing. That is also okay. But the very good design is, you have to make it to 1, close to 1, right? And then, okay, stack of convolutional layer, how many you are including, that is your wish. And then dense layer, you have to add dense layer. Actually this should be done. Dense layer has to be added. In some autoencoders, even in the Keras library model, they have not used the dense layer. Simply flatten. That flatten layer, whatever they are getting, the values, that was taken as the representation vector. Okay, that is also fine. It is just one dimension array, that's it. That is also okay. But the best way is to add the dense layer. You can add a dense layer. Dense layer means our regular artificial neural network layer, that you have to add dense layer and then define the encoder. Now you have added one by one all the layers to the sequential model. Then you have to develop one model, complete model for the encoder. Then you have to go for the next step. Yeah, how we can develop, see this. See here, encoder equal to, I am taking the image size, S is image size I am taking 128. I am taking 128 by 128 image. Actually I have taken this code, this is not my program. Okay, I have taken this from the Keras library. Directly I am taking from the Keras, but I modified according to my requirements. They have given with 28 by 28. 28 by 28, okay, and they have given only 2. The dimension is 100 I have taken, but in the original Keras model it has taken only 2. And I modified according to my requirement. I don't want to use, actually that model was given with the predefined library, predefined data sets like MNIST and other data sets. I don't like to use them. I want to use my own images, whatever it is. I want to use another image. For that, I have written like this. Now, encoder equal to sequential. I am creating the sequential model. Again here, since you have not done the practical program here, I am explaining this. The model, if you want to develop one CNN model, there are 2 ways. One is, you can develop the sequential model or simply model. Sequential model means layer, next to that another layer through the sequential manner. The model is another model available. If you take from that, you can take one layer and you can develop 2 layers. You can give 2 layers and again you can give 2 layers from that. And finally you can combine them and you can get the final output. Meaning that in the multi-way, in the sequential you can go through only one way only. By using the model you can go with different ways and you can come here. It is simple. You can just imagine like this. From your house to college, if you want to come here, if you use the sequential model, you know only one way. Only one way, there is only one way. That is only from house to, signal 1, signal 2, signal 3, cross, that's it, close. If there is the traffic jam, then you can take another way, shortcut. Or even if it is long, you can go through another way. Like this is the model. If you use only one way, that is sequential. If you use multiple ways and finally if you are meeting somewhere, that is called the model, simple model, right? And here for autoencoder we need sequential is enough. Sequential is enough. You can use model also, right? Even if you have the number of ways, even if you know number of ways, you can use the same way every day, right? So in the similar way, I am using the sequential, it is easy. Sequential is easy to build. If you take the model, it is a little difficult, right? So simple way is sequential and simply we can add the layers. Encoder dot, add of, conv 2D of, I am adding 16 filters. 16 filters. You please think, one image, I am giving one image How many features are generating? 16 features. 16 images are generating. I am giving one image. For one image input, I am generating 16 features. First feature, for the first feature, I am giving the kernel size is 3 by 3. So, first time it will take the 3 by 3 and 3 by 3 will move over the image and it will create one feature. Second filter, second 3 by 3, it will move on the image and will create second feature, third feature, fourth feature. In that way, total 16 features will be generated, meaning that 16 images will be generated. From one image, 16 images are generating, right? And from those 16 images again, from each image, each of the 16 image, I am adding one more layer with 32. From each 16, from 16 we are generating 32 again and we are increasing because we are moving depth, right? And in between we have some more concepts. See here, for this I am taking the activation as ReLU. I am taking the activation ReLU. Why we are taking ReLU? The activations also very important. While taking the activation, you have to keep it in mind what is your aim. We are making it down step by step. If you are following the regular rule that you have to come to the one by one, then there is no need of this. But if you are stopping in the middle of the process, let us say for example from 128 to 128 by 128, if it comes to let us say for example 32 by 32, then if you flatten it, again on the other side you have to reshape it. You are flattening and again you are going with the dense, and on the other side again you have to regenerate the same image. So again you have to reconstruct, meaning that you have to reshape. If you follow strictly the rule that you have to come to 1 by 1 pixel, then you need not worry. Otherwise you have to remember what is the shape before flattening, that you have to see that. Required shape equal to encoder dot output shape. From this layer, what is the output shape that will be taken and it is storing in the required shape. And then encoder dot add of flatten. After that we are adding the flatten. And then we are adding the dense. Dense of, what is the size? That is the size of the vector. Representation vector. This is the representation vector. I am taking that with Z dimension. And activation is ReLU I am giving. Hope you understand, right? Now, say this. This is the model, convolutional, conv 2D input, and then conv 2D batch normalization, conv 2D batch normalization, conv 2D batch normalization, flatten, and then dense. This is the architecture of the network, encoder network. And decoder network. Decoder, same. You have to construct input to the decoder. What is the input to the decoder? What is input to the decoder? Encoder's last dense layer. Encoder's dense layer, last dense layer, that is representation vector. The representation vector will be the input for this. And you have to take it back into the shape, original shape. So, for that, connect input to the dense layer and reshape the vector to a tensor that can be reproducing the original image. Reshape it. Already we have stored that. We have stored that. The shape of the output, right? And then stack the convolutional layers and then define the decoder. That is over. Next step, this is the same. Decoder I am taking new sequential, and decoder that add convolution, batch normalization, convolution, batch normalization, convolution, and so on. But one more thing, convolution, conv 2D transpose, not convolution here. Conv 2D transpose, reverse, upsampling. It is not downsample, it is upsampling. Conv 2D transpose, for decoder you have to use conv 2D transpose. Otherwise you have to use upsample plus conv 2D. Right? So this is what we are getting. After this is the autoencoder. We have to train this. See here, before training we have to combine these two. We designed the encoder separately, decoder separately, and we have to combine them. So I am taking one more sequential model with autoencoder. Autoencoder that add of encoder, I am just adding the encoder, and here I am adding one more dense. And then reshape. I am using the reshape here. Actually that there we can remove. Okay, and then add of decoder, and then I am getting the summary, and this is the layer. See here, input image, sequential layer, and then dense, reshape, and sequential decoder. And so this is how to plot the model. This is the plotting the model. See, this is the encoder, this is the decoder, in between there is the reshape, dense and reshape between that. I think it may not be visible, and we will share the slides, you will get it clearly, right? And you can use this also, plot model of, anyway you will execute this program, I am giving you the link, you will execute this program. Okay, and how can we compile? Once if you develop the model, you have to compile. In CNN we have explained, right? We have to compile the model with optimizer. Optimizer I am taking Adam, and then loss equal to MSE. Why we are taking this MSE? Actually it is a regeneration error. Reconstruction error it is called. Actually it is the MSE. Why should we take MSE? Because the output is also the pixel. We are giving the input pixel, output is also the pixel, that is from 0 to 255. So the difference is, since it is the regression like environment, we have to go for the MSE, mean squared error. Hope you understand, right? And after that, fit the model. Now here you have to understand whether you want to regenerate the same image or another image, that you have to decide at this moment. If you want to regenerate the same image, while trying the model, fit the model, x comma x, input is x, output is also x. So you are giving the image and you are expecting the same image back from this model. What is the use? Compress the image, send to somewhere over the network, and you can regenerate the image. That is the use case of this encoder. And if you want another model, let us say for example, you want to give the black and white image and you are expecting the color image, then this you have to change. Of course, according to that, you have to change the model also. How you have to change the model, that I will explain. Okay? And then, yeah. Now we are predicting. Y hat autoencoder at predict of, I am giving one image so that we will get one image, regenerated image. Now these are the two links. Okay, you can, I think you have the Kaggle, right? Do you have Kaggle? You don't have Kaggle? Okay, you just do one thing. Open the kaggle.com in your laptops and search for P.V.N. BALARAMA profile. In that, all these codes are open. Okay, you just open kaggle.com. In that, search for my profile P.V.N. BALARAMA. Okay, in that, search the codes. In that, there will be the codes. In the codes, you find the autoencoder. This is the thing. Or directly you can type this. basic auto encoder. Basic auto encoder, you can open this in your laptop. And if you want to use the GPU, you have to register with your mail ID and also your phone number. Did you get the code? Any one of you? Did you get the code? In Kaggle. There is no time to make you write the program. So I am giving the code directly. So you can use my codes. You just open my profile, you will get so many codes for ANN, CNN, and so many projects are also there. Okay, you can take them as the examples. Okay, so let us see here. Yes, first we are taking the TensorFlow. It is a library for the neural network. Okay, and as the part of the, actually in the old version we have the TensorFlow and Keras, two libraries. The Keras can work on two environments, that is, one is the TensorFlow, another one is the Theano. So these are the two libraries. On top of those libraries the Keras was built. Okay, and the next version of the, that is from 2.0 version of TensorFlow, the Keras was added as the module. So you need not use the Keras separately. Directly you can import the Keras through TensorFlow, right? So you can see that TensorFlow.keras.models import sequential. I am using sequential only here for autoencoder. And conv2d transpose, dense, input layer, flatten, and all these we are using. And this is the designing of the encoder without batch normalization. Without batch normalization, we are creating the encoder. Okay? And then you can see the architecture of the encoder by using plot model in the Keras library. In the Keras utils, we have the plot model. By using this, you can plot any type of model, any model you can develop, and you can see the architecture easily in the graphical form. So see here, this is a model what we have built, the encoder, and then we are just giving the reshaping. We are just reshaping. We are not using any dense layer separately here. Directly we are reshaping. We have connected to the flatten, and then directly we are reshaping it to the required shape, and then conv2d transpose. We are giving the 3 conv2d transpose. In encoder we have given 3 conv2d. In the decoder we are giving 3 conv2d transpose layers, right? And now we are connecting, now the model, we are plotting the model. This is the complete model, and now we have to compile. We have to compile the model. Compile, the optimizer is Adam. Directly you can give within the quotations Adam. Otherwise you can give that keras.optimizers.adam. You can give any one of them. Directly within the quotations, if you give the Adam, that will be taken with the default parameters. If you want to change the parameters, you have to go with a TensorFlow.keras.optimizers.adam of, you can give the learning rate and all, right? So loss function, loss is MSE, and metrics to display, that is also MSE. Now I am loading the images. What are the images I am taking? So see here, the images what I am taking is, I will show you the images also. Yeah, see here, these are the images what I have taken. These are the images what I have taken. See this is the image. So all these are the various images I have taken. I want to reconstruct the same image in the basic model. Okay. Yeah. And I want to load all the images. I have given the code for loading the images. This is the Python program only. You can analyze this to load the images. Once if you load the images, you will get the X value. See here, I am calling this method X equal to load gray images of. I am passing that folder. All the black and white images are in gray images folder. So I am just giving this. So what the function will do is, it will read one by one images and it will be converted into the NumPy array and it will store as the very big NumPy array with all the images. 3-dimensional NumPy array. Right? So X is, see, if you see the image shape, that you can understand. 200 images, 128 by 128 size and only one layer, because it is the grayscale. Black and white image needs only one layer, 128 by 128, that is enough. Okay. Now model.fit, I am just running 10 epochs only. Okay. And I am giving the X and X, only X and X I am giving. So I want to give the black and white image and I want to get the black and white image only. Whatever the image I am giving, I am expecting the same. So the model is trained and this is the original image I am taking. See here, I am taking X of 0 means first image. I am taking the first image. Okay. And I am displaying that this is the image what I am taking. Okay. And then this is the regenerated image. This is the regenerated image. The original image and regenerated image. Definitely there will be some loss. There will be some difference. Definitely. See here, little blurred. See how many epochs I run. Only 10 epochs. If I run 100 epochs, then it may change. The clarity may change. Right? So this is the black and white. And this is another program, black and white to color. I want to give the black and white picture and I want to get the color picture. So for that, what I have to modify is, see here, in the decoder, actually for the black and white only one layer is required. For color image, how many layers? 3 layers required. So output of decoder should give 3 layers. Output of decoder should give 3 layers. So you can see that decoder. See, this is encoder. Encoder I am not changing much. For the decoder, you can see that last convolutional transpose filters equal to 3. If you see the decoder of the basic autoencoder, for this you can observe that the filter is the number of filters. This is 1. You just observe this. See here. Did you observe? See that. Number of filters is 1 for the basic autoencoder which regenerates the given image. Okay. And for the color image, black and white to color image, here it is 3. 3 layers. Right. Now I ran this program and I executed. Right now I don't have that much time to execute. It will take much time for execution. Okay, see here, this is the complete picture. Whatever I have shown you there. This is the complete picture. This is the encoder. This is the input. The dotted line, this is the encoder. After encoder, there is a dense I am giving, and then decoder. After decoder, compiling. After compilation, I am loading the images X, loading the color images. I am loading the color images Y equal to load color images. After that, see Y shape, already we have seen the X shape, 200, 128, 128, 1, because it is black and white. Color image is having Y, 200 images, 128 by 128 and 3. This is the original images, already they are available. Already they are available in the input. Okay. Now fit the model. I ran 500 epochs. Okay. I ran 500 epochs. After completion of 500 epochs, yeah, after running 500 epochs, this is the black and white image, this is my input, I am giving the input, and this is the expected output, this is the expected, already it is existing expected output. After 500 epochs, how my model is predicting is like this. Say this, after 500 epochs, if you increase the number of epochs, it will increase the clarity, and all those small dots, actually I ran nearly 5000 epochs. After 5000 epochs, I got a good color picture. I don't have that much time here now. Okay, 500, after 5000 epochs, I think I ran that 5000 epochs 2 times or 3 times, I don't remember. After that I got very good color picture. It is almost looking like the original picture. Right? So there are small color dots, that's it. Only color dots are added. But if you run the number of epochs, you will get the color picture correctly. Right? So this is the auto encoder part. Now I want to go with the next one. Yeah. Yeah, I think this is over. Now use cases. The black and white picture, we can give the black and white picture and we will get the color picture. Auto colorization. You can take the old movies, any old movies, your favorite movie. If you have your favorite movie, you can download that movie and you can make it as the frames and you can apply this model and you can enjoy that movie in color if you are able to build that model. Right? And another one, old images, our old photos, right? They may be damaged, and if you want to restore them, you can restore by using this autoencoder. You can get like this, but more patience is required to train. Number of times you have to run the model and you have to change the optimizers, you have to change the activations, you have to try with different combinations, then definitely you will get the good output. It is not an easy task. Patience, more patience is required. Right? Now, variational. Now let us enter into the variational autoencoder. This is the concept of original generative AI. Till now we have done simply convolution and deconvolution, that's it. But now, without any information of originality, if you want to develop from the random, if you want to generate the images from random, then that concept is started from variational autoencoder. What is this concept? Let us see here. See here, in this, we have, instead of, actually here we have one dense layer in the autoencoder. Please listen, in the autoencoder we have only one dense layer. But here we will have two dense layers. From the flatten, we will take two dense layers. And one is the mean vector. Mean vector means if you have a picture, in the picture actually the dense concept, the representation vector concept is take the random positions. If you give 100 random positions, with those positions you have to generate the image. That is the autoencoder. Here this is same. Whatever we are seeing this here, mean vector, it is same as our autoencoder. In autoencoder representation vector is there. The same thing we are using here also. But this is the additional vector. It is the variance. What is the difference between the mean and variance? Mean is a single point. Variance is spread. How far it is spread? The data distribution is spreaded. That variance means it is spreading, how spreaded it is. That will be the variance vector, and we will take that variance vector with the normal distribution. Why should we take the normal distribution? The normal distribution can represent the data very efficiently. Simple. Inga depth don't go in depth more. Okay. So normal distribution, it can represent the data in efficient way for analysis. So in general, for any machine learning or deep learning algorithm, we will convert the given data into normal distribution in most of the cases. And see here, next. Now these two layers will be combined and it will give a sample layer. A sample will be taken from these two layers. Okay. Now this part is called the latent space. In that there is the mean vector and variance vector, and this is called the latent vector. This vector sample, whatever the sample we are taking, that is called the latent vector. And how we can generate that latent vector? For that there are some formulas. By using these two vectors, we have to create this. How can we create that? That is by using, this is Z. Z equal to mu plus sigma epsilon. Sigma means here variance is there. Okay. Variance. Log, apply the log on the variance and take that. And epsilon, you will give the epsilon also. What is this epsilon? It will ensure that it will be in the normal distribution. The epsilon will make that into normal distribution, random normal distribution. Right? Now see here. Now what is sigma? See here, sigma equal to, it is the sigma square. That is the same thing. We are applying exponential and log. It will be the variance vector. That is also called the log vector. We will call it as the log vector. Okay. Now how we can combine these two is like this. Z equal to mu plus sigmoid and epsilon. That epsilon is the here. From that we can generate the complete image, and that is the encoder and this is the decoder, and there is the back propagation on that Adam. We will take the Adam in general optimizer. And what is the loss? Previously what we have taken the loss? Mean squared error. Mean squared error. I think all of you know mean squared error. In IML it is there. Mean squared error. Further regression. The mean squared error is called here reconstruction error. Right? Now the same we will take. Because of this, the same MSE will be there, and for this there is a separate loss will be there. That is VIE loss, the total loss equal to R loss plus KL loss, KL divergence. We will call it as the KL divergence. If you want to go in depth in the KL divergence, we have to go with so much of mathematics. Okay, this is the structure wise we are going with the architecture wise. You just go through this. I will show you what is KL divergence also, right? Now, this is the total architecture of variational autoencoder. Why we are taking this here is, see here, this variance. Why we should take the variance vector? Here there is a reason for that. So, variational autoencoder will take, there are two changes. We have to change the encoder and loss function. Change the encoder by adding two vectors instead of one vector, one representation vector. We have to add two vectors and we have to change the loss function also. These are the two changes required from autoencoder to variational autoencoder. Now what we are changing that, let us see. See here, in the encoder, actually in the autoencoder we will take only one point. By taking one point we are generating the entire image. Sometimes it may give very good result. Sometimes it may give very good result. Sometimes it will give you something else, right? But if you take the surrounding, same concept of convolution like that, instead of taking the single point, if you are able to take the surroundings also, if you are able to considering the surroundings, then it is variational. You will take the variance. Not only you are taking the point, one point, around that point you are taking some area, right? So that is the, see here, this is the autoencoder. It will take only one point and it will generate this. Instead of that, variational autoencoder, it will take the normal distribution of that from that point, from that mean, as the center of that mean, it will take the variance from that, from any point of this, it can be easily generate the image, regenerate the image. So, for training it may take some time, but generation is very easy, right? Now, how this normal distribution can be represented? The normal distribution, it can be represented with mean and variance. This is mathematical term, right? For these two, to represent these two, we are having two vectors. Already you have seen mean vector and variance vector, two vectors we are using, right? Now see here, in this, see here, mu, mean vector, mu, and log vector, that is the variance vector, we are taking these two, and instead of taking a specific point, we can take that, and if you want to combine these two, we are taking z equal to mu plus sigma epsilon. The sigma epsilon, sigma is it representing this, and what is that sigma? There is a formula for that sigma again. Again there is a formula for sigma, we can take that, and epsilon, what is the epsilon? It is the random normal distribution. In the normal distribution we will take some values and we will combine them, right? From here onwards, generating the image from the randomness was started. In the next step, we will go with the GAN. In the GAN, we will remove this also. Completely from random, we will generate the images. How we will see, how we will generate that, we will see in the next session. Okay? Now, and of course, this is the same thing whatever I am discussing from last half an hour. Okay? Now, sampling. Now, how can we combine that sampling? For that, we are creating one sample layer. For sampling, we have to combine two layers, right? How can we combine? There are some operations again. We have to take the mean, we have to take the variance, and we have to apply some rule, that is the normal distribution. We have to take the random normal distribution, and also we have to combine them. There are lot of stuff. So for that I am creating one class sample, and in that, for that I am taking inputs. We are taking the inputs. What are the inputs for the sample? There are two inputs. One is the mean vector and second is the variance vector. Two vectors we are taking as the input, and in that Z mean and Z log vector equal to inputs. So those two will be given into this, and batch equal to, and dimension, batch and dimension. This is to find the dimension of the normal distribution, how much we have to generate the normal distribution with dimension. With the batch and dimension, that is also depending upon the Z mean. Of course, these two are, we are taking these two are the same. So Z mean of 0, Z mean of 1, meaning that the mean vector size, how much is the mean vector size, the same thing we are taking. How much it is, the same we are taking. Of course, without flattening also we can do it, but it is in the next level, not here. In the experimental and in the research level you can try with that without flattening also, that is the next level. So because of that reason here 0 1, 0th shape of 0th element, 0th dimension, it is in the batch. Shape of first dimension is in the DIM, so that we are creating the normal distribution epsilon, and we are applying the same values onto this formula to generate this red color layer. Now once if you generate this, then you can go with the generation of the encoder, complete encoder. We just defined the sample. Now we are creating the encoder with, see, convolution, all are same. Only here there is the change. After the dense here, from there I am taking mean, log vector and then sampling. So you can observe that here. From here it is taking two places, two ways, and it is the mean, it is the variance, again we are getting the sampling. Because of this reason it is not sequential model. It is not the sequential model, it is the neural network model, that's it. It is not sequential. Because of this different ways, right? Now, the decoder is same. Decoder, you need not change anything in the decoder, same. Okay? Now, loss function, reconstruction loss, it is MSE only. Kullback-Leibler, it is the KL divergence. See, all the loss functions are developed only to find the difference between two values or two vectors or two matrices, whatever. Two data sets, simply we can say that two data sets, the difference. It may be the cross entropy, binary cross entropy, categorical cross entropy. Like this, there are so many metrics are there to find the differences. One of the differences is KL divergence. In that, what is KL divergence? I cannot explain it at this moment. It is okay. It is very big concept. Okay, only to find the difference. Instead of using the cross entropy, we will use the KL divergence, right? And see here, and then KL divergence, how we can calculate that? There is a direct formula we are giving. Okay, actually the formula is like this: 1/2 sigma 1 plus log of sigma square, that is variance, minus mean square minus variance square. This is the formula. The formula directly we will apply that here. 1/2, it is 0.5 and so on. Right? These are the loss function. In this way we can find the loss function for any model. You can go for the GAN, you can go for any model. You have to understand the architecture, you have to understand the activations, loss functions and optimizers. Right? What is the optimizer? At least you should know what is that. That's it. What is that? If you know, that is enough. As I told you, you need not go for the agriculture to eat rice. At least you should know there are several types of rice. Right? In that way you have to understand what are the different concepts available. Now, To define that, I am defining the loss function like this. Okay, first R loss and then KL loss, that is a KL divergence, and then total loss. Total loss we are giving by combining these two, R loss plus KL loss. By combining those two, you will get the final complete loss of the variational autoencoder. But defining these two are tricky little. This is okay, R loss is okay, KL divergence. Through that KL divergence concept, we have to apply that formula. At least what is that formula you have to understand, that's it. Right? And you can try with another thing also. You can try with categorical cross entropy. You can try with categorical cross entropy. Right? And so this is what, and program is also there. Please wait, I will show you the program also. Right. So we can combine the encoder, decoder, and we can use the reconstruction error for the autoencoder, and for variational autoencoder we have to use two loss functions. For the autoencoder only one vector, for the variational autoencoder two vectors, we will take the representation vectors, and loss functions, for the autoencoder there is only one loss function, for variational autoencoder there are two loss functions. Okay, that is what you have to remember and you have to understand, but you have to execute the programs. Initially you have to try to reconstruct the same image. Second attempt you have to try with color to black and white to color, so that you will get, definitely you will get, after 15,000 epochs or to 20,000 epochs I got the result for this. It has taken nearly 1 hour I think. Okay, I will show you the program, and I don't know whether that output is there or not. Yeah, this is a variational autoencoder. The same thing we are having. The coding is little different. See here. This is what we are taking. I think I have shown this on the slides only. This is the main point here. This is the main area where we have to concentrate for the variational autoencoder. And yeah, and then loss function. Then we have to concentrate on the loss function. And one more thing, yeah, one more important thing here. Loss function we can define in two ways. One is we can define the class for the loss function and we can define all the functions. That is one way. Another way is inside the model, inside the model there is a function called generation step or train step. Train step function is there, meaning that every time whenever you fit the model, the training is progressing, this function will be called. Sometimes it is better to define this loss function inside that function. We can override that function and you can define your own loss function to for the gradient descent concept, for the optimizer, not only gradient descent, for any optimizer. So you can define that here. In this program, I have given two programs. Basic variational autoencoder, you can find that in my profile. Basic variational autoencoder, in that I defined the method. Okay, and another program I used the train step. Okay, both the codes are available. You can go through them and this is working fine. For that we have to tune more. After one epoch, what it is happening, I will tell you the problem also. In the separate defining of the loss function, what is happening is, after one epoch, it is becoming as the NAN values. It is giving NAN values. Meaning that somewhere there is some problem in the translation of the tensors. So we have to find it and tune it. If we take some time and tune it, it is okay. But anyway, this is working fine. Inside the train step, we can define the same function, so it is working fine. There is some compatibility problem because in this program we are using two libraries. One is TensorFlow, second one is Keras. There may be the compatibility problem, right? So because of that reason we are getting that problem, even though it is working for some epochs. After some epochs it is giving the error, meaning that vanishing gradient, we have to handle it. For that we have to spend some time, that's it. It is not the meaning of not working, it is working but we have to tune. But this it is working for any number of epochs, you can go through it. See here, I think I have run this for 500 epochs. I will show you the result. This is the original image, black and white image I am taking. I am expecting this after 500 epochs. Not expecting that image, the same image I am expecting. I am expecting the same image, this. Okay, because the training step, oh, again I have to go back. No, I don't want to go back. So, the same image I am expecting, after 500 epochs, this is generating like this. Some shape is giving. If you run, actually I have executed this, after 10,000 epochs or 15,000 epochs, it is giving the good picture. I have seen that. Okay. And I will show you the training also, so that fit the model X data and X data only. X data and X data, meaning that regenerating the same image. For color image, it is different. I will show you the color image also. No, it is another program, denoising. Denoising program is also there, and it is also there. The black and white to color image for variational auto encoder is also available in that notebook. Okay, you can go through it. Okay, so this is the concept of auto encoder. This is what I want to share. Actually, there is more. Actually, I have to make you execute that, but time is not permitting. So, I am giving the code. Please try to execute. And if you have any questions, you can come back again. We will be here only. So, we will clarify the doubts.